Hello guys, welcome to another episode of Cuda Education. Today we want to paint the sky red and maybe some other colors. Okay, so we're going to paint the sky red and we're going to learn some things about CPU GPU relationship and how all of this application works. So first of all, I have to make sure I put things back to the way they were. So let me do that first. So 295. So what we're going to do is we are going to first, we're going to put things back to the to default so you guys remember how um, things are done. Just know for now that we are in the update state function, but let us just run the application now. And as we know it to be before, so we have a baseline. Okay, so we're running the application and we have our baseline, right? So we have everything that we know from the default application, and we could zoom in and out and we could see all of that stuff, right? But we're gonna paint this guy to be a different color. Okay, we're gonna paint this guy to be a different color. So basically the sky is gonna be a different color. Okay, and there we have it. We have our wonderful sky. Okay, all right, the sky is going to be a different color. Okay, so let us go back to our application, and then now we're going to paint the sky red. Okay, so now we are going to run our application. Actually, no, let's not do that. Let's not do that. We got to do 0 here and 0 here. Okay, so now we're going to run our application. We're painting the sky red. And here we have our red sky, right? So we could see that the sky is now red, right? And if we go all the way up the escalator, we could see that the sky is red. Okay, now the thing is, we could have a bit of fun. We could do another color, and we'll see that we get a different color for our sky. Okay, so as you guys can see, we now have a different color for our sky. Okay, we have a different color for our sky. Okay, and we'll just do it one more time, right? And we'll have yet again a different color. So we're hacking our way into getting the sky to be a different color, right? And we see that our sky is a different color and all of that good stuff, right? And we see that our sky is a different color again, right? Real spooky stuff right here. Okay, all right, so you guys had your fun now, so you're obligated to watch the rest of the video, right? Okay, so let us put things back to the way they were, just so you know. I have a bit of sanity for each everything that I do. Okay, so we're back to what we normally expect, right? And you guys could see that we're back to our normal situationship, right? So okay, all right. So we have this update state. We have this update state function updates the GPU copy of buffers for the current frame. Okay, but we kind of have to start from the beginning. Let us start from the beginning. So the topic of this video is basically CPU GPU data flow. Okay, so CPU does some stuff and it eventually makes its way to the GPU. We understand in the previous video that we had 3 frames that were in play, right? One of the frames, ideally, one of the frames is actively being presented to the screen, so we could see, what was done to the frame, and we see it on the screen. And then the other two frames are sort of in play. They typically could be modified by the CPU. Data could be transferred onto them. Drawings, things could be updated, all of that stuff with the other two. But for the actively displayed frame is protected. It cannot be modified because we are actively displaying it to the screen. It cannot be modified, right? And we use this semaphore construct in Apple Metal in order to protect it, to make sure that the CPU doesn't try to actively modify it while it's being presented to the screen. In the previous video, we did tinker with that model where we allow the CPU to actively modify the frame that's being presented to the screen, and we saw that there was flickering and data corruption and all that stuff. If you want to see that, first of all, just understand there's a flicker warning, right? The image is going to flicker, the application is going to flicker, but you're going to see what we did is we collapsed the number of frames that were in play from 3 to 1, so it was just the one frame that was being worked with by all the systems, by the CPU and the GPU. And then we also disabled the semaphore. So the semaphore, again, protects synchronization. So if one is working on the frame, the other one can't work on it. We disable that synchronization restraint. And that is why in that particular instance, the frame showed a lot of corruption, a lot of flickering, a lot of things going on, because we only had one frame, number one, and then number two, we didn't have any synchronization going on. So the CPU is literally actively, things are literally actively being modified as it's being displayed to the screen, right? Again, flicker warning. You could watch the previous video and the previous episode to see what's going on. Okay, so here we're now talking about, we're diving into this CPU to GPU data flow situation, right? So this is where so this update state function is where the renderer actually feeds GPU information every frame, right? So this function is the CPU to GPU bridge, okay? So big picture, every frame the CPU computes camera matrices, time, fog density, sun direction, shadow matrices, debug totals, light counts, etc., etc. Then it writes them into a metal buffer. So when we say metal buffer now, we're kind of talking about GPU side stuff, a buffer that the GPU either can access, and basically GPU side stuff, right? The GPU reads that buffer in every shader stage, okay? So where does this frame data live, okay? So the frame data lives, now we are in renderer AAPL. We're in the AAPL renderer file, right? Renderer AAPL renderer. And now we're in the update state piece of it. This is line 2145. But then if we go to the section where the frame data is, this is internal structure containing data for each frame. Multiple copies exist to allow updating while others are in flight. This line right here is talking about our 3 frames that we have going on. So multiple copies exist to allow updating while others are in flight. So while the others are in flight, being presented to the screen, we could actually update stuff, okay? Now, the thing that you have to understand is, and this gets very subtle and nuanced, so you have to kind of pay attention. This code and everything that we're doing here in this particular file is CPU side stuff, right? So this AAPL frame data is a CPU side structure, okay? Within it though, so we have lighting data, point lights buffer, spotlights buffer, lights params buffer, all of this stuff, right? And we also have an MLTL, a metal buffer, frame data buffer, AAPL constants for this frame. Now, the thing is that this piece right here, this piece is so the structure, the sort of this container is sort of, on the CPU side, but these MLTL buffer stuff, it's this is on the this is sort of a sort of, pointing to like the GPU side stuff, right? So we also have frame data view and buffers for each view, ICBs and chunk call information for each view, right? But this metal buffer, MTL buffer, this is sort of GPU side stuff, okay? So we have um, each in-flight frame. So each in-flight frame has its own copy of this thing, right? So when we talk about how we're presenting to the screen and then we're also modifying stuff, when we're presenting to the screen, this stuff is frozen, right? Because we're not going to actively modify things that are being presented to the screen. The frame is already built and we're presenting to the screen, and it's being presented to the screen. We're not going to actively modify. But for the other two frames that are not actively being presented to the screen, we are modifying stuff. We are updating stuff. And again, every frame the CPU computes camera matrices, time, fog density, sun direction, shadow matrices, debug toggles, light counts, etc. Then it writes them into an MTL buffer, a metal buffer, right? An MTL buffer, right? The GPU reads that buffer in every shader stage. So I just want to anchor you guys back to exactly what's going on. Right. So this AAPL frame constants, right? It's a very important it's a very important thing. This AAPL frame constants, and it is in Um, it is in one second. It is frame data common to most shaders, right? So AAPL frame constants, okay? So this strut, frame data common to most shaders, okay? So this strut right now um, is shared between the CPU and the GPU, copied into frame data buffer, and bound in nearly every shader. And it contains a bunch of stuff that basically um, the shader can access. Okay, this is the brain of the frame. Okay, so we have, screen size, physical size, sun direction, sky color, um, all of this stuff. Okay, so this is the brain of the frame, right? So this particular piece is what sort of puts frame data common to most shaders, right? So when we say shaders, guys, we're talking GPU side stuff, right? So just to get back to thing, we have our APL frame data, which is sort of a CPU side struct, but then we have our APL constants, frame constants, um, which is associated with every frame and is more GPU side stuff. But to anchor you guys, let's just move forward for a second. No, I don't want to do that. I don't want to do that. To anchor you guys, let us just give me a second, guys. Uh, okay, so let us go back to So inside update state, right? Inside our update state function, updates a GPU copy of buffers for the current frame, right? Um, update frame data. Okay, so here we're updating frame data, right? So we have APL frame constants, frame data. Here we're updating. This gives its CPU access to GPU memory. Okay, so here is where we're trying to basically update the contents of the buffer that the GPU can see, right? We assign this frame data variable right here, and this frame data variable is what's being manipulated. Um, it's what's being manipulated to give us our sky color, right? So we're literally accessing GPU memory from, we're accessing GPU memory from, we're accessing GPU memory, using this line right here, frame data buffer constants, right? Right, so you're writing into GPU memory. Now, the thing that you have to appreciate with this is that there's no copy call is required. These buffers are, um, the CPU and the GPU share memory on Apple Silicon, so there's no copy call required. Because we're accessing the data on the GPU directly, and this is what the shader is using. This is what the shader is using to this is what the shader is using in order to basically do what it needs to do. So in shader files, you basically see that these assignments are being used. These assignments are being consumed by the shader so that it could generate the frame. Right? So this frame data variable is very important because it is what connects CPU to the GPU and allows the GPU to read the buffer, right? And you could basically see that it's a bunch of stuff that is basically updated with this construct, right? So we're not gonna, right? So we have one big frame constants buffer, and you know basically CPU GPU can interface between the two. And on Apple Silicon, this memory is shared, so there's no explicit copy call or anything like that. It's just done. It's basically done. You just update the memory, and the GPU can read that information and get sort of the information that it needs. So let us just do a quick anchoring again. So we are in the update state file, and we have our APL frame constants, update frame data, right? And we have this frame data variable, and it's basically going into the APL frame constants, GPU visible memory, and it's updating all of these. It's updating all of these, all of these variables, including our sky color, right? So this right here is being updated through the frame data, which is accessing the GPU, visible memory. Um, Internal structure containing the data for each frame. Multiple copies exist to allow updating while others are in flight. So all these MTL buffers, right? Um, all these MTL buffers is things that the GPU, this is stuff that's GPU visible, right? So we could, the GPU can access things within these MTL buffers. This frame data buffer, I want to. Right, so notice that, frame data buffer, right? So again, I just mentally I want to, yeah, so this is a GPU accessible buffer, and again, we are we are literally trying to basically, you know, modify we're basically trying to modify this thing because this is what this is what is an MTL buffer, and the GPU can access that stuff. So the CPU, just so we can anchor ourselves again, the CPU updates memory. It does not call send to GPU. It does not call upload. It just writes into a mapped buffer, and that mapped buffer is this guy right here, right? The GPU reads it later when executing the command buffer, right? Meadows synchronization model guarantees safety because triple buffering prevents overwrite. So that triple buffering means we have 3 frames, and while one is being presented, the other 2 can be modified, right? So Meadows synchronization model guarantees safety because triple buffering prevents overwrite, and command buffer execution is ordered, right? We didn't really get into command buffer in this episode. But we'll get into it. But now that we have that information, let us actually play around with our sky color again, right? So you guys know now, you guys have an understanding of what's going on with the CPU GPU relationship, right? So now we're basically modifying our frame data stuff, and we could see here that we get a different color again, and I don't know, is this even a thing? But this frame data is basically going into the CPU is going into the CPU is going into GPU. The CPU is going into GPU, the metal buffer, and modifying changes so that we have a different outcome for what's going on. Okay, and just wanted to anchor you guys again, just so you guys see how we could get creative with this stuff, right? So we have this. It's actually a pretty cool color, right? Can't complain. This is actually a pretty cool color. But anyway, and then when we put it back to default, we get our thing that we normally know, right? So we get back our normal application. Okay, so you can see how the mood of everything changes just based on how the color of the sky changes. Okay, so let us continue with our investigation. So um right, so each one of these things, this frame data buffer, right? Each frame has its own frame data buffer, right? So each frame has its own frame data buffer, and we're updating the sky color in the frame data buffer, and we know that this is a metal buffer, and we have this APL frame constants that we right, we have our AAPL frame constants that frame data common to most shaders, right? So we're updating all of this stuff, including the sky color. This is where the shader consumes the data, and you know, we have we have we're able to modify things. So we have 3 copies of that. The semaphore ensures that we never overwrite a buffer still being used by the GPU. So, so just as an overall big picture, the CPU runs update. The CPU runs update state. The CPU runs update state. Okay. And it writes into the MTL. It writes into the MTL the frame the contents, the frame buffer contents, and then the GPU shaders read APL frame constants, right? So the GPU, reads those values. No magic, just memory. So just to reiterate, the APL frame data is a CPU side container for per frame metal resources. Okay. So APL frame data is a CPU side container for per frame metal resources. So notice that we have the metal buffer here, and we also have some more buffers down here, but we just care about this one because this is where the light, the sky color was dictated. The APL frame constants is a GPU size struct that lives inside of one of those resources. So I believe it lives inside of this guy, right? But notice that this APL frame data is CPU side, right? But the CPU side structure, this structure points to metal buffers, right? And this is where this APL frame constants is where, GPU side, and it's visible, it's visible by the GPU. Now, I believe that like these things right here, I believe that these things right here aren't necessarily visible by the GPU. So it's not on the piece of memory that is shared, piece of Apple silicon that is shared between GPU and CPU. It's just CPU side. But all these metal buffer stuff is visible also on the GPU. So one, the APL frame data is an engine management structure. The other is shader input data, right? So AAPL frame data owns the metal buffers, and AAPL frame constants is the data written into one of those buffers, right? So yeah, we're writing AAPL owns the metal buffers. So sort of CPU side owns these buffers, and inside of this buffer, APL frame constants is the data written into one of those buffers, right? So we saw that with our sky model, we're changing the CPU is changing the color of the sky in the frame, and we're changing it inside of the metal buffer, which is GPU side. Okay. Um. Yeah, I just every time I have to go into this, I don't know. Right. So every time I have to go into this GPU side, this AAPL frame constants. Okay, so we're now on GPU side. This is what the shaders consume. And every time I say shader, guys, I'm talking GPU side stuff, right? We are in the AAPL shader types. So once we see shaders, we know we are in GPU side stuff, right? So that stuff, this structure contains things like, all of these variables right here, right? All of these variables, right? Including our sky color, of course, because that's what we visibly see on the screen. This strut is shared between CPU and GPU, right? Used in metal shaders and bound as a constant buffer. And we'll get into that stuff later. The um, so that's APL frame constants, right? APL frame data. This strut, the strut itself exists only on CPU, is not shared with shaders, is not included in .metal files, and is not visible to GPU directly. It is purely an engine side frame slot manager. So yeah, I mean the strut itself, CPU side stuff, but notice that we have plugs into the metal buffers, which is CPU and GPU visible. So I mean the language is a little bit strange, but just know that this strut in its entirety is CPU side, but we have slots to modify buffers that the GPU uses and the GPU consumes, right? And it consumes it in the form of the shaders that it uses. Um, and these two worlds, the APL frame data strut and the APL frame constant strut, is connected. It's connected by our update state friend, right? So it's connected by this function right here. Um, so we have a reference to a current frame, right, which is the current frame that we're working on. Remember, we have 3 frames and there's a current frame. um, the frame data buffer, right? So the frame data buffer is our metal buffer, right? The frame data buffer is our metal buffer, and dot constants gives you CPU access to its memory. So the frame data buffer is the metal buffer, and then dot contents is what allows us to basically have access. The CPU gives the CPU access to the memory, right? So notice that we run with this frame data variable because now we have access to the metal buffer memory, right? And we use that frame data to deal with the sky color and all that stuff. And then there's a casting thing. You cast it with this guy, C++ stuff. you know um, so why they are separate types? This separation is deliberate and very clean architecture. APL frame data exists to manage triple buffering, hold metal resources, keep per frame allocations separate, and avoid CPU or GPU CPU overwrite hazards. So let us go back to so AAPL frame data exists to manage triple buffering, hold metal resources, keep per frame allocations separate, avoid GPU CPU overwrite hazards. Okay. Um, I keep having to. Right, 205. All right, I'll remember that. Okay, APL frame constants exist to define shader visible data layout, right? So this is shader visible, GPU stuff, visible data layout, right? Be shared between C++ and metal. So basically, this is shared between the CPU side stuff and the GPU side stuff, right? And provide a stable memory contract, right? Um, why this design is powerful? It's powerful because each frame has a copy of this stuff. So you have frame 0, frame 1, and frame 2. And each one has its own frame data buffer. So frame 0 GPU reads frame data buffer index 0. Frame 1 CPU writes frame data buffer index 1. And frame 2 CPU writes frame data buffer index 2. So while frame 0 is being read, frame 1 and frame 2 is actively being written to and instructions are being placed inside of it so that when the GPU renders, it renders what we want the updates to be. There are no collisions. This is a direct connection between step one, semaphores and in-flight frames, and step two, per frame constants. We're not going to get into that. But I think I've hammered the point in enough in this episode. Again, I'll say AAPL frame data, engine bookkeeping, owns buffers, CPU only. APL frame constants, GPU contract, shared header, used in shaders, right? So APL frame data manages frame resources. APL frame constants is the actual data written into one of those resources and consumed by shaders. And that's it for this episode, guys. I yeah, I think we have done enough for this episode. So we'll go back to baseline just to see what is what. And I know you guys are clamoring, so I will do one more modification on the sky color bit, but you guys have to remind me to put it back. So we're gonna have to get into all of these variables and stuff like that. Let's change this to 7, okay? And let's see what we get. Cancel. I have to stop it and then run it, okay? And we get our woo. Yeah, now this is really scary, right, guys? This is really scary. Okay. All right. Let's just do 2 and 3 and 3. Let's stop and let's run. All right. So you guys still get this situation here, okay? But yeah, guys, that's what we have going on here. Now I gotta make sure that I get back to baseline. I can't mess around with that. You don't want to start off with a modified situation, right? So we're back to what we normally know. Anyway, guys, thank you for watching. This is Cuda Education. Support the channel, tell your friends, get a group of your friends together and work on this stuff. Make 2026 count, learn metal in 2026, parallel processing, GPU programming, AI, machine learning, deep learning, all of that stuff. You're going to need a GPU to do this. This stuff will teach you GPU programming, high performance computing, all of that stuff. So support the channel, like, subscribe, comment below, tell me what you think. And let's take advantage of 2026. Time is expensive, so make good use of it. Thank you for watching. Have a great day. This is Cuda Education. Also, guys, they still haven't updated Xcode. They still haven't updated the App Store to Xcode 26.3. And of course, guys, you guys want to be able to run your agentic coding tools in Xcode, but you can only do it if you have Xcode 26.3. If you need to do that, the only way you could get Xcode 26.3 is if you sign up for your free Apple developer account. Log into the developer portal, download the beta version of Xcode, which is 26.3. The current version on the App Store is 26.2, but you want the beta version 26.3. It's also called the release candidate. You download that. Make sure you update your macOS operating system to the latest operating system. Make sure that you have Apple Intelligence enabled. And then once you do that, you could click this star button thing, and you could start, have the agentic coding stuff help you with, defining stuff, finding where things are declared or defined, all of that stuff. Now, the default for the agentic coding feature in Xcode is it comes sort of pre-built with access to Codex, which is the Chat GPT um, model provider, and Claude, which is the Anthropic model provider. Now you can add a third party model like for example Gemini, but you need an API key and all that stuff. For my situation, basically, in order to have your Xcode to be able to run Xcode, you need a paid account with ChatGPT. So if you have your paid account, then you could run Xcode inside of. I mean, you could run Codex. You could run Codex inside of Xcode. Okay, so Codex is the model provider from ChatGPT, and you'll be able to run it. The thing is, if you don't have a paid account with ChatGPT, you can still integrate. Sort of, you'll have your ChatGPT prompt, access to your ChatGPT prompt, so you could maybe like copy code into the ChatGPT prompt and sort of do stuff, but you're not gonna really get. I believe you don't get full application awareness, and like it knows where all the files are and where things are declared. It's not gonna know all that stuff. It's just gonna be a standard issue ChatGPT prompt. So like, as if you were running ChatGPT in your browser, right? And you were like pasting stuff in and asking it about different features or different commands and stuff like that. But you want the codex piece of it. I don't know anything about the Claude portion of it. The Claude is a whole different a whole different world. But I do have experience with codex, and I've done previous episodes where we talk about codex and all that it does. But yeah, guys, we're making 2026 count. We are already in February, so you guys know that things are things are moving. We're already in month 2, so by the end of 2026, we want to be well versed in Metal. This particular application is Metal 4, so that means that you kind of have to have modern Mac hardware. I mean, I'm running on an M4 chip, but I think you could run it on a couple other M chips, but I'm not too sure. This particular application, the Hello World, the Hello Triangle application is it can run on regular Metal, but we are focused on Metal 4, which you need modern hardware. So you got to check to make sure that your Mac can run Metal 4, right? Because this is a Metal 4 application. Because it's dealing with modern rendering, right? That's the name of the application, modern renderer. So that's all that stuff. Anyway, guys, long video, but we covered a lot of stuff. We're kind of getting comfortable with how things work and why things are the way they are. Have a great day. Goodbye.